Hi, welcome back to my class in Calculus 1 or Differential Calculus. In our last meeting, we took up the first limit theorem and we stated that the limit of a function exists if and only if the right-hand limit and the left-hand limit of the function are numerically equal. And this theorem, we said last time, is a biconditional statement or an if and only if statement. And for today, we will continue with the limit theorems that we will apply when evaluating the limits of functions. But before that, those who missed the first lessons in differential calculus, please search for my videos, Art Teaches Calculus 1, Differential Calculus. We now go to the second theorem actually, on limit of function. So this is actually our second theorem. The limit of k as x approaches a is equal to k. In this theorem, k here is a constant. And for all succeeding theorems that we will take up today, the functions f sub 1 of x, f sub 2 of x, f sub 3 of x, up to f sub n of x are functions of the independent variable x. So we let f1, f2, f3, f sub n be functions, and we let k, k1, k2, k sub 3 up to k sub n be elements of the set of real numbers. So these real numbers k, k1, k2, k3 up to k sub n are constants. Such as in theorem 2 that says the limit of a constant as x approaches a is equal to the constant. In our function notation, y equals f of x, in this theorem, the function f of x is equal to the constant k. So comparing these two imply that y equals f of x, but f of x equals k. So y equals k by transitive property of equality. The transitive property of equality says if y equals f of x and f of x equals k, then y equals k. So our function here, y equals f of x, is a constant function. This means that for any value of the independent variable x, the value of y, or the value of the function for any value of the independent variable x, is equal to the constant k. We can sketch the graph of this constant function in the Cartesian plane, where we write y, the dependent variable, in the vertical axis, and we write the independent variable x in the horizontal axis, and the point at the intersection of the horizontal and the vertical axis is denoted by point 0, or the origin. Now the constant k here can be any number in the y-axis. Suppose this is k. The graph now of the constant function is the constant function such as y equals k is a horizontal line that will pass through this point on the y-axis and is parallel with the x-axis and is perpendicular with the y-axis. Again, the graph of a constant function y equals k, and supposing this is the constant k on the y-axis or vertical axis, the graph of a constant function is a horizontal line that will pass through this point on the y-axis and is perpendicular to the y-axis and parallel with the x-axis. So we draw that line passing through this value of y equals k on the y-axis. It's perpendicular with the y-axis and is parallel with the horizontal axis or x-axis. This is the graph of the constant function y equals k. And you can see from the graph that for any value of x on the horizontal axis, the value of y is always k. That's why we call it constant function. And suppose this is a in the second limit theorem. As x approaches a, either from the left or from the right of a, the value of the function or the value of y approaches k. And you see there is no break in the graph of the constant function at x equals a, because when x is a, the value of y equals k. Thus, the limit of the constant function k exists, as indicated by this point, which implies that there is no break in the graph of the constant function when x equals a. Thus, for any constant function, the limit of the constant k as x approaches a equals the constant. We take an example. We find the limit of square root of 2 over 3 as x approaches negative 1. In this example, our constant k is the root of 2 over 3 and a is negative 1. And by this limit theorem 2, if you take the limit of a constant as x approaches a certain number a, the limit is equal to the constant. And in this example, the constant is square root of 2 divided by 3. Therefore, by this second limit theorem, the limit of square root of 2 over 3 is this constant, square root of 2 over 3. Example 2, we find the limit of pi over 5, 2 pi over 5 as x approaches 0. In this example, pi is a constant. It is an irrational number with value of 3.14. It's actually a non-terminating, non-decimal real number, pi. So pi is a constant, multiplied by 2, it's a constant, divided by 5 is a constant. Thus, 2 pi over 5 is a constant. And we find the limit of 2 pi over 5 as x approaches a. In the second limit theorem, your k now is 2 pi over 5. And the second limit theorem says that the limit of a constant as x approaches a is equal to the constant. Thus, the limit of this constant, 2 pi over 5, as x approaches 0, is equal to this constant, 2 pi over 5. That's the second limit theorem on the limit of function, where our function is a constant function k. We now take the third limit theorem for some specific function. This theorem says that the limit of mx plus b, this is now our function. In our function notation, y equals f of x. Our function of the independent variable x is now given by this linear expression mx plus b. Mx plus b. And then by transitive property of equality, we say that y equals mx plus b. This function f of x equals mx plus b is what is known as the linear function because the exponent of the independent variable x is 1. And more particularly, this is a linear equation in x and y. More specifically, this is the equation of a line in slope-intercept form, where the coefficient m of x is the slope of the line, and b here is the y-intercept, or the intersection of the line, whose equation is given by this linear equation, and the vertical axis y. Going back to this limit theorem 3, the limit of this linear expression mx plus b as x approaches a is equal to ma plus b. When evaluating the limit of a linear expression of this form, the variable x is replaced with this number a, the number to which the values of x are approaching. Simply replace x with the number a, and you get the limit of this function mx plus b as x approaches a. If you will sketch the graph of this linear equation in x and y, the graph is a straight line. And supposing b, the constant b is not zero, the line will intersect the y-axis at b. Suppose this is the graph of the linear equation y equals mx plus b. Because we assume that the constant term here b is not zero, the line intersects the y-axis at y equals b. B is the y-intercept of the line with this equation, or b here, y equals b, is the point of intersection of the line and the y-axis. If x approaches a, say this is the number a. If you evaluate this function f of x equals mx plus b, or if you substitute x equals a into this linear equation, we get ma plus b. And that point, the point with coordinates a and ma plus b is a point on the line. This will be the point A, axis A, and the value of y is ma plus b. As x approaches A, either from the left or from the right, the value of the function approaches ma plus b, as what the third limit theorem says. And you can see that because the limit of this function mx plus b exists as x approaches a, it is represented geometrically by this point, by the graph with no break at this point. That is, the graph of the line is continuous at this point. And we will take up more of points of continuity and discontinuity of a function over a given interval later on. We now take an example for the application of this limit theorem 3. Example, we have limit of 7x minus 5 as x approaches 1/2. In the third limit theorem, this is now your mx plus b, which means that m is 7 and b is -5. And x approaches a in this limit theorem 3, a now is 1/2. And to evaluate this, to find the limit of this linear expression, just simply replace x with a. Hence, in 7x minus b, to get the limit of 7x minus b as x approaches 1/2, we simply replace x with 1/2. We get 7 multiplied by 1/2 minus 5 equals 7 times 1/2 is 7/2, or 7/2 minus 5. And the denominator of 5 is 1. And the LCD of 2 and 1 is 2. And we find the numerator, LCD divided by the denominator of the first fraction. 2 divided by 2 is 1, multiplied by the numerator 7. Minus, we said that the denominator of 5 here is 1. We find the second term. LCD divided by the denominator of 5, 1 is 2. Multiplied by 5 is 10. And we simplify the numerator, 7 minus 10 is -3 over 2. And this is the limit of 7x minus 5 as x approaches 1/2. If you let x to approach the number 1/2, the value of the function or the value of y will approach this number, -3/2. Consider the following example for which we will apply the third limit theorem, the limit of mx plus b as x approaches a, which we said earlier is equal to ma plus b. We evaluate the limit of 3 minus 1/2 x as x approaches -2. In this given, the function mx plus b is the linear expression 3 minus 1/2 x, where m now is, the coefficient of x is, m is -1/2, and the constant b is a positive constant 3. In this limit also, a in the third limit theorem is now -2. And by limit theorem 3, to find the limit of a linear expression such as 3 minus 1/2 x, simply replace x with -2. And we get 3 minus 1/2 multiplied by x. Our x is the a, to which the values of x approach. A is -2. And we simplify, we have 3. Negative times negative is positive. And 2 divided by 1 multiplied by 2 is 2, divided by 2 is 1. And 3 plus 1 is 4. Thus, the limit of 3 minus 1/2 x as x approaches -2 is 4. That means if you let the values of x approach -2 either from the left or from the right of -2, the value of the function, the values of the function or the value of y, which is given by 3 minus 1/2 x, will approach the number 4. Now we will take the fourth limit theorem, which is a generalized form of the third limit theorem. In the third limit theorem, we have a linear function in the independent variable x. But in limit theorem 4, our function now is a polynomial function in the independent variable x. So the exponent of x here can be 1, can be even a constant. The polynomial function x can be a constant, a linear function, a quadratic function, a cubic function, or a function in variable x with the highest exponent of more than 3. So the limit of polynomial function in x as x approaches a is equal to p of a. This means that when you evaluate the limit of a polynomial function as x approaches a certain number a, you simply evaluate the polynomial function at x equals a. So this means p of a means that in the given polynomial function x, polynomial function p of x, you replace x with a and you simplify the resulting expression. We now take an example for applying limit theorem 4. Consider the following problem. Evaluate. To evaluate means to find the limit of the given function as x approaches a given specific number. Evaluate limit of x cubed minus 2x plus 7 as x approaches negative 2. In limit theorem 4, our polynomial function in x is now this cubic expression, or our polynomial function is a cubic function in x, and p of x equals x cubed minus 2x plus 7. And x approaches a in theorem 4 is now equal to negative 2. And to evaluate the limit of this cubic function as x approaches negative 2, limit theorem 4 says that you simply evaluate the polynomial function at x equals a, which means that in this cubic expression you replace x with negative 2. And we do that. This is now equal to x is negative 2 to the power 3 minus 2 multiplied by x. X is negative 2 plus the constant 7. You simplify the right hand side by property of exponent. The cube of negative 2 means you take the cube of negative 1 multiplied by the cube of 2. And the cube of negative 1 is negative. And the cube of 2 is 8. For the second term, we have negative multiplied by negative is positive. And 2 by 2 is 4. So we write plus 4. And the last term is positive 7. And we add negative 8 plus 4 is negative 4. Plus 7 is 3. Thus, the limit of our polynomial function or cubic function x cubed minus 2x plus 7 as x approaches negative 2 is 3. That means if you let the values of x to approach negative 2 either from the left or from the right of negative 2, the value of y given by x cubed minus 2x plus 7 will approach the number 3. And this point negative 2 and 3 is a point on the graph of this cubic equation. Geometrically, in the graph of this cubic equation, we'll have no break at the point negative 2 and 3, which means that the graph of this cubic equation is continuous at the point negative 2 and 3. And that indicates that the limit of the cubic function exists as x approaches negative 2, and the limit is 3. In our last example, our polynomial function is given by x cubed minus 2x plus 7, and we evaluate this limit as x approaches negative 2. In evaluating this limit, we apply the limit theorem 4 for the limit of a polynomial function in x as x approaches a. Another way to evaluate this limit is to consider each individual term of this cubic expression as a function, and you get the limit of each individual function as x approaches negative 2, and then combine the limits by the operations indicated in the given expression. We will now state that as another theorem, the limit theorem 5, known as the limit of a sum, or difference of two functions. This limit theorem 5 says that the limit of a sum indicated by addition or difference indicated by the minus sign of two functions, say f sub 1 of x and f sub 2 of x, as x approaches a is equal to the sum or difference of the limits of the two functions as x approaches a. So the limit of a sum or difference of these two functions, f sub 1 and f sub 2, as x approaches a is equal to the sum or difference of the limit of the first function, f sub 1 of x, as x approaches a, plus or minus the limit of the second function, f sub 2, limit of f sub 2 of x, as x approaches a. Again, the limit theorem 5, or known as the limit of a sum or difference of two functions, states that the limit of a sum or difference of two functions, say f sub 1 of x and f sub 2 of x, as x approaches a is equal to the sum or difference of the limits of the two functions given by limit of f sub 1 of x as x approaches a, and the limit of f sub 2 of x as x approaches a. We now take an example for applying this limit theorem 5, the limit of a sum or difference of two functions. Consider the following problem. Evaluate limit of sine squared theta minus 3 cosine theta as theta approaches pi over 2. The first term of this expression, sine squared theta, is the same as the square of sine theta. So you may rewrite this limit of sine squared theta minus 3 cosine theta as theta approaches pi over 2. We rewrite this as the limit of sine squared theta is the same as the square of sine theta. Sine theta squared minus 3 cosine theta as theta approaches pi over 2. So here we have the limit of the difference of two functions. The first function in the limit theorem 5 is the square of sine theta, and the second function is 3 times cosine theta. And by limit theorem 5, the limit of the difference of two functions is equal to the difference of the limits of the two functions. The limit of sine theta squared as theta approaches pi over 2 minus the limit of 3 cosine theta as theta approaches pi over 2. And we write that as the limit of sine theta squared as theta approaches pi over 2 minus the limit of 3 cosine theta as theta approaches pi over 2. Now evaluate each limit by simply substituting pi over 2 for theta. Here in sine theta squared, replace theta with pi over 2. In the second term, you replace theta in cosine with pi over 2. And we get sine pi over 2 square minus 3 times cosine, replace theta with pi over 2, cosine pi over 2. And we get sine of pi over 2 is 1, pi over 2 is 90 degrees, and sine of 90 degrees is 1. And raised to 2, 1 squared minus the cosine of pi over 2 is 0, or cosine of 90 degrees is 0, multiplied by 3 is 0. Hence minus 0. And 1 squared is 1 minus 0 is 1. Thus, the limit of sine squared theta minus 3 cosine theta as theta approaches pi over 2 is equal to 1. In the next Theorem 6, we will now generalize Theorem 5 by stating the limit of a sum or difference of more than 2 functions of n functions. We now state the generalized form of limit Theorem 5, or the limit of a sum or difference of 2 functions. In limit Theorem 6, we now have the sum or difference of more than 2 functions. We actually have n functions. Limit Theorem 6 states that the limit of f sub 1 of x plus or minus f sub 2 of x plus or minus f sub 3 of x plus or minus up to plus or minus f sub n of x as x approaches a is equal to the limit of the first function f sub 1 of x as x approaches a plus or minus the limit of the second function f sub 2 of x as x approaches the same number a, plus or minus the limit of the third function f sub 3 of x as x approaches a, plus or minus up to plus or minus the limit of the nth function f sub n of x as x approaches the same number a. So the limit Theorem 6 states that the limit of a sum of 2 or more functions is equal to the sum or difference of the limits of these 2 or more functions. The next theorem is for evaluating a function raised to some exponent n. And limit Theorem 7 states that the limit of the function f of x raised to the power n is equal, as x approaches a, is equal to the limit of the function f of x as x approaches a raised to the power n. So to evaluate the limit of a function raised to an exponent means that you get the limit of the function f of x and you raise that limit to the exponent n. We now take an example for applying this limit theorem 6 and 7. For applying limit theorems 6 and 7, consider the following problem. Evaluate limit of 3 times e to the power x minus 2 ln of x. This is of course an exponential function, and this is a natural logarithmic function plus the square of cosine x over 2, and this third term is a trigonometric function. And we find the difference and sum of this as x approaches 0. We find the limit of this as x approaches 0. And by limit theorem 6, that says the limit of a sum or difference of 3 or more functions is equal to the sum or difference of the limits of these 3 or more functions. Hence, the limit of this difference and sum is equal to the difference and sum of the limits of the first function, the second term, and the third function. Hence, the limit of this is equal to the limit of the first function 3e to the power x as x approaches 0 minus the limit of the second function, the limit of 2 ln x as x approaches 0, plus the limit of this third function, the square of cosine x. Cosine x square over 2 as x approaches 0. And to evaluate each limit, each of these 3 limits, we simply replace x, substitute 0 for x, or replace x with 0. And we get 3 multiplied by e to the 0 minus 2 ln of 0 plus replace x with 0, cosine of 0 over 2 to the power 2. E is not equal to 0, and by property of exponent, a non-zero base raised to an exponent 0 is 1. E here is actually an irrational real number, a non-terminating, non-repeating decimal number. So e to the 0 is 1, multiplied by 3 is 3. And ln here is the natural logarithm. It's a logarithm to the base e. And ln of 0 is 1, multiplied by negative 2. 1 times negative 2 is negative 2. And 0 here, cosine of 0 is 1 over 2 raised to 2. Cosine of 0 is 1 over 2. That's 1/2. Square is 1/4. And the denominators of 3 and negative 2 are 1. And the LCD of the denominator 1, 1, and 4 is 4. And we find the numerator by dividing the LCD by each denominator and multiply the result by the numerator. 4 divided by denominator of 3 is 1, multiplied by 3 is 3. Minus 4 divided by denominator of negative 2 or 2 is 1, multiplied by 2 is 2. Sorry, the denominator of 3 here is 1. 4 divided by 1 is 4. Multiplied by 3 is 12. The denominator of 2 here is 1. 4 divided by 1 is 4. Multiplied by 2 is 8. Plus, denominator of the last term is 4. LCD 4 divided by 4 is 1. Multiplied by 1 is 1. And we simplify the numerator. We have 12 minus 8 is 4. Plus 1 is 5. Divide by 4. 5 over 4. This is an improper fraction, and you can always write this as a mixed fraction by dividing 5 by 4. Hence the limit of this function 3e to the x minus 2 ln x plus the square of cosine x over 2 as x approaches 0 is 5 over 4. In the next lesson, we will take the limit of a product of two functions and the limit of a product of more than two functions and the limit of radical function. And we will take more examples for the applications of these limit theorems. If you have questions about the lessons today, you ask your questions in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison. Thank you.